Hello, everyone, and welcome to Talk Nerdy. Today is Monday, August 12th, 2019, and I'm the host of the show, Cara Santa Maria. Now, before we dive into the show, I want to thank those of you who made Talk Nerdy possible this week. And unfortunately, while I'm recording this introduction, Patreon is down for scheduled maintenance, so I can't call you out by name this week. I'm so sorry. But I promise that I will again next week. But for now, I just want to thank everybody who has gone to www.patreon.com/talknerdy and pledged your support of the show. It really does mean an awful lot. It's the main source of revenue for the show, and it's how I get to keep on going week after week. All right. I guess that's kind of the business end of this. Why don't we go ahead and just introduce the show and dive right in? So this week I had the opportunity to talk to Molly Strausbaugh, and she's an assistant director at the Chemical Abstract Service, otherwise known as the CAS, or if you're a chemistry student, you might have called it the CAS. It's actually a division of the American Chemical Society. And what they do, it's really interesting, actually. They identify, aggregate, and organize all publicly disclosed chemistry information. So they've basically created this valuable collection of content that is available to researchers, patent professionals, people in industry, students, across the board, if they need to know something about the, basic chemistry of all these different products and solutions. So we're going to talk about that. We're going to talk a bit about the periodic table, but mostly we're going to talk about what chemistry is and why it matters, because you know what? We don't talk about chemistry enough on the show. So this week we're going to do just that. Without any further ado, here she is, Molly Strausbaugh. Well, Molly, thank you so much for joining me today.
Thank you for having me, Cara.
So I'm excited to talk all things chemistry and the periodic table. Now tell me, this year was the 150th birthday. Birthday, that's a weird thing to say. Anniversary, maybe? I don't know, of the periodic table of the elements, right?
Yes.
And so what does that actually mean? I mean, the elements have been around a lot longer than that, right?
Sure. But what this means is that this was the first real, there were some other attempts at organizing them, but this is the one that we basically use the framework today. It starts to tell us about, its organization tells us about the elements, and it can start to tell us what their position tells us a little bit about their properties and give us an idea a little bit of what they do. And how that was put together in its construction is what we're celebrating in 2019.
How did we decide to go with the structure that we have now? Because I do feel like it's not uncommon when I'm digging around in science archives or looking at news stories for the week that there will be a little featurette written about other options for the periodic table, or even new options that some people are playing with, like spiral shapes and star shapes and different things like that. How did we stick with the structure that we now know and love as the periodic table?
Part of what the organization is about similarities. So if we look at similarities with atomic weights, and then we start to see that we have some similar chemical properties. And so that's a little bit more about the organization of why that's important. And it gives us information as we start to work with some of those chemical elements that comprise substances and ingredients that we put in products that we make today.
Okay, so a lot of that really came down to kind of what we deemed as useful for us as people, because of course elements exist in nature. They existed long before we existed. Some of them we've had to synthesize, but many of them exist in nature. So it was really kind of our human conception of how we feel like they should be organized.
Well, it's based in fact. So we know things about the different elements. So we know what their atomic weight is. We can learn about their properties. So once they have been either discovered or synthesized, there are things that we can do to look at how they interact with other elements, how they interact just in nature. What kind of things do they do? What about them? And so that organization starts to be a lot of benefits because you start to see what groups and what families have things that are similar, what things have similar weights, and what can that mean that we do. So what if we look at it another way, we can look at it like a trend and say what things are similar, what things have trends, and what can I learn about these things, or what can I use. So if I want to start to make a product, or I can look at what elements and how are they composed into a chemical structure, and what would that tell me about what that actual substance on a bigger level would do or how it would behave.
Gotcha. Okay. And so before we dive in, I think more to kind of the joys and the wonders of chemistry and why it is that probably we shouldn't have all slept through it in high school, I would love to talk to you about why it is that I'm talking to you about this today. So you are, let me see what your actual title is. Okay, so you're a chemist and assistant director of CAS, and CAS is a division of the American Chemical Society. Tell me a little bit more about CAS.
Sure. So CAS is an information solutions provider. So if we say, okay, well, what does that mean? Well, if I'm a chemist or a scientist, I have a lot of questions, and I have research I need to do, whether that's in a laboratory or I'm helping someone as an IP professional and I want to help them secure a patent, or I'm synthesizing something, or I'm making a new product that I can find on the shelf. So if I'm going to be the one that makes Tylenol, for example, I need to know some things. So I would need to know what are some of the properties of the ingredients in Tylenol? How would I synthesize an active ingredient? What's sort of state of the art research in pain relievers? Who's a thought leader? What other trends are we seeing? Do I have some white space? So we can help you answer those questions. So what we do is curate and retain scientific information. So we're looking at patents, journals, other publicly available information sources about chemistry. And we're saying, what's the important things here, and what can we start to tell you to answer your questions? So we have a 110-year history, and so how we've done that has changed over time. But today we have products like SciFinder that a lot of synthetic chemists use, that they can start to answer questions about how would I synthesize something? I need to find out a reaction pathway to work out a synthesis. How can I get those questions answered? And so our goal is to help scientists answer their questions to further their research and make products that we find in the market today. You may also have seen the last time you painted a room with a paint can, you might have seen by the ingredients a number, and that's a CAS registry number. And that is kind of the ticket to finding information about the ingredients, each ingredient that's in that can of paint. So looking that up can tell you what is a boiling point? What is a melting point? What are the other properties? Is it regulated somewhere? There's tons of information that comes along with that registry number that helps you understand the identity of the chemical substance and its properties, and what else is being done with it, what are other people doing with it, and what are some opportunities for me to do something with it.
Oh, that's fascinating. And so obviously you are working in this kind of intersectional role where I'm looking here, and it looks like you have an MBA and you're working in this obviously chemistry heavy profession. What made you interested in doing chemistry, and kind of how did you take that turn through business and chemistry?
Sure. So I started out always wanting to study chemistry as a young child with my chemistry set that my dad bought me, and doing experiments at home. And it was always very fascinating to me. It was always challenging, and the things that you could create. And one thing I found that as I progressed through school was that I also liked computers and technology, and I liked math. So a good fit for me was looking at CAS and saying, how can we share chemistry information that is out there, and what are ways that we can make it available to people, and how can I help with that? So I get to use a computer every day, and I get to use my science skills. With my chemistry education, I did learn a lot about scientific content and gaining that knowledge, and I learned about process. When I took the turn to business, some of the challenges that we face at CAS is how do people want to see chemical information? So, and that changes over time as technology evolves. What we can provide for people evolves too. And so part of the business education is, how do I start to understand the consumer? So my goal is to reach other scientists and chemists and present them information in a useful way. But sometimes the chemistry background doesn't always provide that element of learning. So from the business side, learning how to optimize processes, how can I get things and more information and products available to consumers faster in a way that reaches them? How can I work with them to find out what their needs are? So that instead of saying, well, I'm the scientist here, I know exactly what you need, I'm not in your lab every day, and I'm not in different industries every day doing that work. But there are plenty of people who are. How can I start to work with each of them, talk with them, ask them questions, and start to discover what their needs are, and how can I deliver them value?
What a fascinating job. How long have you been doing this?
About 16 years.
Oh, wow. Okay. So this is your career. This is what you've been really focused on and curating and building up throughout your life.
Absolutely. And it's not the same job that it was 5 years ago or 10 years ago. That's the nice thing about how fast information technology moves and how fast science moves, is that I'm never bored here. Every day is a challenge. And with each innovation that comes out, how can we make things better? Part of it is learning quickly and adapting and going forward and taking on those challenges. So when I started here, we definitely were an information technology company, and now we're moving into solutions. And solutions means we can start to bring in more technical things. So we can start to look at predictive technologies, data analytics, and data derivations, and make those things available too, versus just saying, well, here's what was directly reported in the literature. We can start to say, here's what we know from what's been reported previously and many times, and we can start to predict, we can start to look for trends, and we can start to say, well, it looks like certain chemical substances behave a certain way. How else can we present these in a way that is more useful to people in a lab?
So, I mean, I have to ask because obviously, when it comes to these chemical substances, like you mentioned, these solutions, these compounds, there's a million different words for the sort of the IP, I guess, that you're learning about and describing and curating and all of that. So, I mean, these are the building blocks of everything that we know, and of course, they're utilized in different ways by industry, but how can you possibly have a decent handle on so much information? Like, are there people at CAS whose job it is to focus on certain types of chemicals? Are you more in the sort of curation and information solution segment? So you don't really have to know everything there is to know about every single chemical. It just seems so vast. And the old kind of adage that when you start your education, you know a tiny amount about a whole lot. And then as you specialize, you learn a whole lot about very, very little. Which end of the spectrum are you on in your position?
I feel like I retain a lot of the big picture views. So for me, I work both on the content side and I also work on the product development side. So I have a unique seat within CAS that both I'm involved with. How are we going to curate this? How should things enter our database? What kind of policies should we have to make sure that we're representing chemistry in a good way? And then I also have a seat at the product table saying, okay, we have all this data that we've collected. What is the best way to accurately represent it in a way that different scientists need? So what does an IP professional need? What does a synthetic chemist need? What does a professor need? What does a formulator need? What do people in different roles in chemistry and science need? And how can we take that data and present it to them in a way that helps them do their job and innovate faster?
Mm-hmm. Yeah.
So how do we curate all of this information? We have about 600 scientists on staff.
Whoa, really?
Yes. Yes.
So wait, do they work there full time, or are they also professors and run their own labs and then they're like part time working with the AF?
No, they're all full-time employees here. That Yes. So they have a very tough job in looking at literature. So you mentioned a little bit, Cara, about how do you organize and how do you get very specialized? Well, one of the things that we would say has changed in science over the last 2 decades is how cross-disciplinary it has become. So part of our role is how can we be specialized, but also have enough broad knowledge that when we see publications that are cross-disciplinary, that we can curate them quickly and appropriately and make them available. So what we typically do is to say, well, what areas of content are pretty similar? And that's where our analysts will specialize, is saying, well, I know a lot about things in biochemistry. I can help with that area. And so we do break things down a little bit more beyond that, but that's a place where that group would work together and consult each other as they need to. And we would have a group of synthetic organic chemists. We would have polymer chemists. We have physical and applied chemists as well, with expertise in environmental chemistry and physical chemistry. But it takes that whole group to work together because there is so much cross discipline. But they are reading a lot of literature every day and looking and seeing what chemical substances are in here. Are there any reactions? What is new and novel about this patent? What is new and novel about this journal article? What is important to somebody who's looking for the state-of-the-art research in this area?
It's a lot. I mean, it feels overwhelming and daunting, but of course, because of the organization, probably within the American Chemical Society, within the CAS, you're able to sort of like divide and conquer in that way. And I mean, 600 scientists, that's like an army. It's an army of chemists whose job it is, as you said, is really to just stay abreast of like exactly what's going on in the world of chemistry. It's what a fascinating. Okay, what I'm loving about this right now is that we have people on the show all the time, and we often talk about quote unquote traditional careers and quote unquote non-traditional careers. And a lot of it's about like breaking down those stereotypes that somehow staying in academia, becoming a professor, and running a lab is a traditional career in the sciences, and everything else is a non-traditional career. This is like a very hybrid sort of industry, academia. What would you even call working for CAS? I mean, it's such an interesting opportunity. And I bet you so many people listening right now don't even know it exists.
That's probably true. But I'm sure there are plenty of students and chemistry students in particular, and professors and industrial chemists, as well as government scientists that are well versed with using our products to be able to learn more about that.
Yeah. But don't even know that like that's a potential opportunity for a position. You know what I mean? They're like, oh yes, it exists, but it is made of people.
Absolutely. Absolutely.
Yeah.
Absolutely. We are. It is not just computers here. There are 600 scientists and plenty of technologists here as well to help us operate.
That's really, really cool. And so if somebody's interested, where are you guys based?
We're based in Columbus, Ohio. We have a nice big campus near the Ohio State University. And we definitely have our website, cas.org, and we frequently post positions out there. So if you're interested in data analytics, chemistry, or the IT world, product building, check us out and see what opportunities we have available.
It's very, very cool. So when I first, got an email about the work that you do and about the potential to have a conversation on the podcast, as I mentioned at the very beginning of the show, it was sort of in the context of celebrating the 150th anniversary of the periodic table of the elements. And so we started to mention some of the things about individual elements that kind of point to how we organize them and how we utilize them. And we threw a few words around, and I thought it might be fun to take a step back and talk about what those things mean, like a little chemistry 101, little tiny bit for the listeners who are like, forgot about this on purpose, because chemistry is awesome. And like we said before, it is foundational to literally everything. So let's take a little bit of a minute and I'm going to pull up a periodic table right now. Periodic table, yay for the internet. And I'm going to look at a big picture of a periodic table, and I'm going to look at all the things that are on it. Okay. So when we look at a periodic table, the first thing we see, probably the simplest periodic table, has a letter and a number. Do you want to tell me a little bit about what that letter and that number represent?
Sure. So that letter represents the atomic symbol of the element. So it's a nice little shorthand way for chemists to communicate and say, this is what I mean. So for example, when we look at the periodic table, we see that element number 1 is hydrogen. And so our symbol for that, or our code for that, is an H. So when we write a molecular formula for a chemical substance, we can abbreviate it and use those symbols like the H and use that instead of writing out words.
And so that atomic number really just means that's where it fits in the organizational structure that we as kind of a global society decided made the most sense.
Yes.
And it really has nothing to do with how we calculate things or how we, it really has I shouldn't say nothing to do. It has a little bit to do with the properties of these different elements, but ultimately we have to look at a more, what would I say, a more detailed periodic table to start getting into the nitty gritty. So beyond the symbol and the atomic number, then we actually see something called atomic weight.
We do. We also see in the atomic number, meaning the number of protons that are in the nucleus of that atom. So it starts to talk about that's what starts to give you the chemical properties and the positioning in the periodic table.
And so the number of, let's talk a little bit about what an element is. Maybe we need to actually take a step back from there too. So you guys remember protons and neutrons and electrons and all that good stuff. So why don't you tell us a little bit about, I guess, the basic structure of an element and also how that feeds into how the periodic table is organized?
So an element, basically, when we look at that, it can't be made into something else. So when we think about, we talked about Tylenol earlier. Tylenol can be broken down into a lot of things. So it has an active ingredient of acetaminophen. It has some inactive ingredients that make it into a tablet, make it able for you to swallow it. So we would consider that a substance or a mixture. And then we start to break this down. So we start to get to hydrogen. And that's where hydrogen can't be anything else. Hydrogen is hydrogen. So there's nothing else to break it down into. It has protons and neutrons, a proton and a neutron and electron. Sorry for that. But that's basically what it is there's nothing else to break it down into.
And so ultimately those things can be combined to make other things. But
absolutely,
at their core, we call them elements, or at their most broken down position, we call them elements. Then we can use elements to build things like compounds and solutions, and there are a lot of different kind of euphemisms for I guess special properties of those things. But the elements, kind of as implied by the name, are the thing that can't be broken down.
Right.
And so you said that the atomic number refers to the number of protons that are in the nucleus of the element. What about the atomic weight?
So when we start to look at that, and we see that in the periodic table, sometimes it's towards the bottom of each box of where it's displayed. But that starts to tell us what is the mass, basically. How much does this weigh?
And why does that matter?
That starts to tell us about the protons and neutrons that are in there. And it starts to tell us more about the properties and how that atom could interact.
And so that's really necessary when you are, let's say, how do they actually, I know so little about chemistry. It's so funny. We very rarely talk about chemistry on the show because I think to a lot of people, it feels like basic science as opposed to like applied science, even though there's obviously so much applied chemistry, which we're going to be diving into today. But I think that when we talk about like biology, for example, we make that distinction between quote unquote basic science and quote unquote applied science. So like biomedical science would be more applied science. We're trying to learn about how organisms function within some sort of context so that we can make better judgments about medicine or about psychology or about X, Y, or Z. Do you use the same distinction in chemistry that there's basic chemistry and there's applied chemistry?
Absolutely. So I would say what we've been talking about for a little bit with the periodic table is really your basic foundation. And when you really get out in the lab for most people that are making the products on the shelves every day, so to make that what goes in that can of paint, to make that Tylenol, you're looking a little bit higher, at a higher level. And you're starting to say, well, what are the ingredients that go into this? The thing to keep in mind is that at the basic foundation level is that all of these ingredients are made up of elements. And how they're arranged and how they're positioned and how they react with each other is what starts to give each of those ingredients their properties. And what you start to look at when you want to make products is to say, well, I need things that either do interact, that don't interact, or I need a stabilizer in there that will help something not interact. But understanding the foundation level of what is the composition of each of those substances or ingredients starts to tell you on how things will work together. Will I be able to make something that is stable and I can put on the shelf for a consumer to buy? Or is it not going to be stable enough and it disintegrates before I can get it into a package?
Yeah, that would be important. All right, guys, let's get back to the show. there are really like layers and layers and levels, right? Like first you're going to be looking at the elemental level. And then as we know, you can combine elements in certain ways to form kind of like simple compounds like carbon dioxide, for example, is one carbon and two oxygen, carbon dioxide. And we know about that. But ultimately, in order to make these sort of industrial chemicals or these compounds that are often used for industry, the stuff gets really complicated really quickly, right?
Absolutely. Absolutely it does. And sometimes it can be at this foundational level, sometimes we can take it for granted very easily because we start to go to say, well, I want to formulate something and I start at the ingredient level. And that's where we would start to try to put things together. But we always have to go back and remember the foundation and say, well, how did this ingredient really get its properties? It does come from the point that it is composed of elements and they bring each of their own properties, and how they interact together gives the actual ingredient or substance its overall properties.
And it's just this kind of Russian doll of interactions that eventually, if you're working with a really, really complicated compound with some really strange interactions, you really need to understand it all the way down.
Yes, absolutely.
And so, is that one of the things that you offer at the CAS is helping people understand kind of from the most um, uh, what's the word I'm looking for? From the most kind of foundational level all the way to the most global level, the properties of the compounds that they're working with?
So some of that's more the role of our parent organization, the American Chemical Society. So while our role at CAS is more helping with industrial chemists and synthetic chemists and academia at that level, the American Chemical Society has an education division, and a lot of things that they do to help out is to provide educational materials to teachers at the K through 12 level and at the university level as well, to help with that foundational understanding, to start moving forward to say, here's the basics that you need, and here's some ways to teach chemistry, to make it fun, to make it interactive. And then as people come up through education and continue on, they might do some chemistry in the box experiments. So there might be some ways for them to learn there. And as they start to get into their undergraduate career, that's probably when they get introduced to CAS and they start having research projects from their professors. And that's when they'd first be exposed to SciFinder to say, okay, I was asked to come up with how to synthesize something in the lab, and I've got to work on this so that I can do my pre-lab and that I can go do my experiment. And so that's when they might come out and look through some of our literature searches and do some reaction searching to say, what can I learn about this? Because my pre-lab has these questions and I need to answer them to be able to go forward. And that's where they would get more their first exposure to us. So we're a little bit beyond the foundational level, and we are more at the synthesis and product level of if a company wants to take something to market, how would they do that? How would they start to work on their development to get to their active ingredient? And how would they start to say, okay, now we've picked our active ingredient. We probably need to patent it, can we? And we need to get this into a form that consumers can use. So I need to get this medication in a way that a patient can take it. What do I need to do for that? What kind of things will work well with this active ingredient? So that it is safe, that it is stable, that it's palatable, all those kind of things so that it can be in the hands of a patient and be safe for them to take.
Okay, so you've mentioned SciFinder a couple of times. Maybe we can talk a little bit more about what it is and how it works, like how it's useful for working chemists and also for undergrads and graduate students and postdocs and all that.
Absolutely. So SciFinder is a pretty powerful research tool in chemistry. So the literature that I mentioned earlier, Cara, that we curate, all those patents and journal articles and other publicly disclosed information, SciFinder is a way for chemists to access it. So instead of having to try to read all of those articles, they're able to ask a question and put in what they're looking for. So if they're looking for a reaction, they can start with a reaction name. If they're looking for something conceptual, so if they want to learn more about Tylenol, they can search for Tylenol. And if they do search for Tylenol, they can start to learn about its properties. They can learn about where it's regulated. They can learn about how it's synthesized. They can learn about its solubility. There are many things that they can do. They can look and see what are people doing with Tylenol today versus what have they done over the past years.
So anybody who's, been a student in academia and who's had to write a scientific paper knows that usually when you need to write about something, you're going to go to your university's online library now because it's 2019. Used to not be like this. Used to be like card catalogs and actually literally searching through periodicals. But now you can go to your university's online library, you search for key terms, you start to nest those key terms, you start to get really creative and really good about how to find individual things, but you often run up against difficulty, which is having to pore through actual full text articles to find what you need, and B, certain articles still being behind paywalls because maybe your university doesn't have a subscription to those journals. Does this solve both of those problems?
It solves a good part of it. So part of what we do in our curation is that we look at those articles and we don't just look for the chemical substances that are in there. Those are of key interest to us as a part of our registry system and to being able to tie substances to properties. But we also look for the key ideas in that article. So what's novel? How are these things, what relationship do the substances have to each other? What is being done there? And we curate those. And so part of what SciFinder does is it can take your query and parse it, and it will do the searching of what a CAS scientist has said is important about that patent or that journal article. And it will give you results. So it does some of the work for you. And you can see what our scientists think and why it's important. You can also see an abstract of the article. So what is this something I really want to look at? For patents, we're able to get you to the full text if that's something that you're interested in. And we're also able to mark where we have. So if you're interested in a specific chemical substance in that article, we can direct you right to where it is. There still obviously is a paywall for a lot of scientific information. But this starts to get you into what do I really want to look at? Where do I really need a full text versus reading 50 articles full text. Maybe you're down to reading the targeted 5 that you need to put your paper together.
Yeah, which is really important. You're right. Instead of pouring through and basically paying for a lot of things that you ultimately don't even need. Which is so incredibly frustrating. And I think anybody listening to the show who's been in academia knows that experience for sure. Okay, I do have to ask, though, kind of broadening this out, because I'm trying to think of like the demographic of who listens to Talk Nerdy. And I think that there's a sliver of people who are actively working in academia. Like there are literally people listening to the show right now who are like pipetting under a vent hood, who are like, haha, this is what's happening in my life today. And then there are people listening to the show who are like, I took a chemistry class once. And then there are people who are like, I managed to not remember anything from chemistry and I'm proud of it. And so my question to you is, for the people who are listening to the show who don't work in this industry, who don't work in academia, who don't like ever intend to work in academia, like why should they even care that the CAS exists? Why should they care about the work that you do? Why do you think that this ultimately still should matter to them?
Well, we're all consumers. And so the products that we buy every day, we help the people who make them. So if you have a headache and you want that Tylenol, if you are getting ready to go out to a party and you want to pick some eyeshadow that you want, if you are growing tomatoes in your garden and you want a way to help stimulate their growth, all the products that are available to you and that are on the shelf have come through chemistry. And so the chemists behind those products have to figure out how to innovate. How can they keep coming up with something new? How can they keep innovating so that things are better, things work better, and maybe last longer? All those kind of features are things that they can discover in SciFinder, and CS is making those available. So the products that you buy every day are enabled by SciFinder in a lot of ways. 48 of the top 50 pharma companies use our products, and they see the value in them and helping them drive innovation. So it's ways for them to learn things faster. So we talked about if you were a student and you had to slog through those 50 articles, think if you're an industrial chemist and you're on a deadline and you need to get something to market quickly and you have to read those 50 articles. It's kind of the same principle. So the faster that researchers and scientists are able to see trends, learn information, the faster they can innovate to bring better consumer products to market that we can all enjoy.
So, I think that a lot of times we hear the word chemical, and there's this happens a lot, I think, with science and science literacy, that there are what we think of as technical definitions for things. And then there are these kind of socially prescribed definitions for things like hypothesis and theory. We talk about that sometimes on the show, that they mean something different when you're defending your thesis than they do when you're just having a casual conversation. And one of the things that we see a lot in sort of the skeptic community is poor usage of terminology. And sometimes I think the kind of quote organic advocacy or anti-GM advocacy, or, however you want to put it, individuals talking about how chemicals are bad. And of course, the common response is literally everything is chemical. So let's have a conversation about that. You mentioned pharma, and you mentioned that like 48 out of the top 50 pharma companies utilize your services. And I think it's easy for people to make that connection in their heads that like, oh yeah, drugs are chemicals. But like food are chemicals, like physical water is a chemical. The table in front of me is chemical. You know what I mean? Everything is chemicals. And so how do you think, I don't even know what my question is, but like, how do you think that what can we do to help get that point across? Like, it's so frustrating that basic level of literacy is lacking. And why do you think that it is that people make a big distinction in their minds between like chemicals being things like drugs and everything else being not made of chemicals?
I think one of the challenges is just the word and just the connotation that has evolved over time, that you start to think of the word chemical and just your brain goes to something unnatural. Oh, it must be unnatural. But there's chemicals in the strawberry that I had for lunch.
It's also like, it's so funny. It's the most natural thing there is. Like chemicals are we can synthesize them, but we synthesize them based on the principles and properties of naturally occurring. Okay. Anyway.
Right. And there are many things that are naturally occurring, and we interact them every day. The clothes we chose to wear today encompasses chemistry, encompasses chemicals. The products that we use every day, natural things, our gardens contain chemistry. The tomatoes that we're growing, there are chemicals in there. They're natural, but they are part of that classification.
Literally everything. I mean, it's almost like we sit here and we are stumped to come up with examples, which is so silly because it's because it's overwhelming, right? Everything is chemicals. Like I'm looking around my office and I'm like, the water in my cup, the coffee in my cup, the cup the coffee's in, the book next to it, the computer.
The caffeine in your coffee.
Yeah, the caffeine in the coffee, the breath coming out of my mouth. It's like everything is chemicals. And we make these kind of distinctions and we categorize things, and I think, put valences on them. Oh gosh, I shouldn't use the word valences because it means something different to chemists than it does to psychologists. We put negative and positive connotations on them depending on kind of our moral stance with certain products. And we don't look at that full building block, of course. But one of the important things here is that most of the products that we buy, you mentioned the reason we should care is because we are consumers, and most of every product we buy is founded in chemistry.
Absolutely.
And we're talking, you mentioned a couple of categories earlier. Maybe you can help us with the distinction between those categories. I think you mentioned synthetic chemistry, you mentioned industrial chemistry. Obviously, there's crossover with these things, but what are some of those categories of chemistry that you work with?
So when we start to think about synthetic chemistry, that's where I really think of the core organic chemistry. So how do I synthesize a product that's organic? So like, how would I make caffeine? I think it was one of my organic chemistry labs that I took an undergrad. How would I put that together? How do those reaction mechanisms work? So basically there's a lot of carbon involved, is where we would think of that. Industrial, we start to think of a little bit more applied. So we might be thinking about ceramics. So the things that end up making some of the dishes that we use could be considered in an applied industrial chemistry, the glazes that go on them. We can think about cosmetic chemistry. So the eyeshadow that I put on today or the nail polish that I have, those kind of things is a cosmetic chemistry. There can be synthesis involved. There can be applied chemistry involved of how do I put all the pieces together to make that work. I work a lot more on some of the applied side of how do we put things together? How do we start to make products that can go to the shelf? And so that's one of the things that I work with in our new product development area is to say, how can we help beyond the synthetic? We have a lot of great technology to help synthetic chemists start to create their reactions, find ways to make them work, to optimize them, to start to predict how could I synthesize this. But one of the things that we're working on now is how can we help the next chemist down the line? So the chemist who says, well, I've got the active ingredient that a synthetic chemist has made. Now, how can I turn this into a product that someone's going to use? How can I turn this into a medication that has a sustained release? How can I turn this into an eyeshadow that lasts 6 hours instead of 4? Those are the challenges that they have. And so it becomes, how can we help them to find a solution? So that's where I spend a lot of my time these days, is more on the applied area of how does something make it to, once it's been synthesized as an active, as the main ingredient that's going to make something work, how can I help people take that and turn it into something that's actually on the shelf for a consumer?
I love that. I'm thinking of kind of science Twitter and all of the different scientists that I follow online, and some of the memes and things that come out periodically. And one of the common refrains that I hear from people is that when they tell people what they do for a living, let's say they're at a dinner party or at a bar or something like that, and people ask, what do you do? And I say, I'm a scientist. And then the conversation might stop there, but they might say, okay, what kind? And then they might start to tell them, and then they'll see eye rolls or bored looks or things like that. And it makes me so sad, because I'm sitting here thinking about how rich and diverse even something like specifically applied industrial chemistry can be. Because you're telling me about all of the help, all of the support, all of the assistance that you offer in your role for working chemists who are trying to, like you said, make the drug that has a more extended release, or make the eyeliner that has a richer pigment, or make the, whatever the case may be, the paint on the wall that puts off less VOCs or whatever it is. And it's so sad that I think we often lump these people together into a big bucket because they use the same tools and they use the same machines and the same processes. But every research question is unique and fascinating, and there's so much depth to that. I can only imagine the interesting conversations that you get to have with people who reach out to you every single day.
Absolutely. And so when I talk with some of people that are working as formulators and they're trying to turn something in there, having the conversation where sitting down with a person that's a formulator and sitting down with their synthetic chemist, some of the things and watching the ways they interact are very interesting, because the synthetic chemist says, oh, well, come on, your job's easy now. I've made this reaction. And the formulator is going to say, well, wait a second. This has to be deliverable in some kind of solution, and you handed me an ingredient that's not soluble. I've got to solve that problem. And so watching each person tackle the problems, and they're unique to each discipline. And you're absolutely right, Cara. There is a depth and a uniqueness to each part. And it's not just about, I'm a scientist, we're all the same. It's, I'm a scientist and I'm solving unique problems.
Absolutely. And those problems are not just fascinating, but they're also critical. And so, I think one of the things that I absolutely love about science, that I absolutely love about doing this show and having people like yourself on the show, is the moments that I get to have where I take a step back and I realize, I kind of am able to peel back the curtain, at least for a few moments, to realize how much goes in to the comforts and the sort of typicality of the modern world that we live in. I think we're so used to just having technology around us and having creature comforts around us that we forget about the years of sweat and labor and mental power that goes into producing those things so that they're a little bit more ergonomic, a little bit more adaptive to our needs, a little bit more comfortable, a little bit more health and wellness focused, that like we really live in a world that was optimized by hardworking people who are doing this kind of basic and applied science every single day.
Absolutely. It's very easy as a consumer to take that for granted. Even for me as a scientist, when I turn into the consumer mode sometimes, it's easy to forget that someone made this possible. A team of scientists made this possible. And that's one of the nice things to remember is that it did take a group of scientists and science to make the things that we use every day possible for us to use.
And how cool that you get to work in a position where you're like just constantly reminded of that every day at like a very, very fundamental level. It's just it's such a kind of probably privileged position, but like you said, you have to let yourself remember those things because it's very easy for us to get into a what we call it kind of an automatic vibe as a consumer and just be like, oh yeah, things just are like they just were like just exist like this in nature. And it's like, no, we made them that way through a lot of human ingenuity and many, many years of focus. Molly, I think that at this point, I want to start transitioning to some of the closing portions of the podcast that I have with each guest that I have on the show. I always close by asking my guests the same two questions. So they're kind of big picture questions. And as somebody who's been working both as a chemist, but also as really like I hate the term, a businesswoman. What does that even mean? Gosh.
I'm not sure either.
Right. I'm like, what is that? Somebody who's been working in the, I think, really unique position that you've been working in for so long. I'm fascinated to hear your response. So are you ready for these big picture questions?
I am ready.
All right, here we go. So I want you to think about the future, and I want you to think about it in whatever context is relevant to you right now. It could be your job. It could be something more personal. It could be a more kind of global citizen context, whatever you deem relevant. And I want you to tell me first, what is the thing that is keeping you up the most at night? The thing that you are most like legitimately concerned about, maybe even pessimistic, maybe even a little bit cynical about, the thing you're really, really worried about. But then on the flip side of that, I want to know, what is the thing that you are genuinely looking forward to, genuinely optimistic about?
So I'm definitely more of the optimist, Cara, but
Yay!
But as far as, the thing that would be something to stick in my mind and be something concerning would be to watch sometimes the politicization of some scientific matters. So we have some in the world, some challenging scientific problems that we're going to have to solve in a way through science. And divisiveness is not going to help us solve that. It's about how can we get the right people together and enable them. So get them what they need to solve that. And so that's something that I'm always looking at. To flip that on the optimistic side, one of the opportunities that I have at CAS is to serve on an international chemistry committee. And so part of what I see in that role is chemists from around the world coming together that are committed to solving problems and investigating and collaborating and working together. And that's something that's very important to drive science forward and to drive our society forward overall.
I mean, here. I think that's all I can say to that. Molly, before we close out, is there anything that we didn't have a chance to cover that you think is important to say?
I think it's just important that science is important in our world. And so if you're interested in science, seek it out, ask questions, and be curious.
Oh, yes, absolutely. That's some of the best advice I think that we can give. I completely agree with that. And if anybody wants to learn more about your work, if they want to learn more about CAS, where can they go?
You're welcome to follow us on Twitter at CAS Chemistry or visit our website, cas.org. We have a blog on about how our work helps to solve real world problems. It's very accessible, so you don't have to be a scientist to get intrigued very quickly. To learn more about chemistry, reach out to people who are studying chemistry, who are practitioners of chemistry, teaching high school or college, or check out our parent organization, American Chemical Society, at acs.org.
Awesome. Well, Molly, thank you so much for joining me today. It was really enlightening, and I had a lot of fun.
Thank you so much, Cara. It was a great conversation.
Of course. And everyone listening, thank you for coming back week after week. I'm really looking forward to the next time we all get together to talk nerdy.